Topic 1.6, scientific notation and variation equations. Let's start with numerical prefixes. First, the kilo. The kilo stands for 1,000 or something, or we can say 10 to the third power. We were first introduced to the word kilo in the American vernacular when we had a movie called Miami Vice, and they called the drugs kilos, and I assume kilo meant cocaine. What it actually meant was a kilogram. The drugs were sold by the gram, by 1,000. So they would say kilograms, which means 1,000 grams. Mega means a million, which is 10 to the 6th power. This was introduced somewhere in the 90s when we went from large floppy disks that held our information on the computers to smaller little plastic ones that are about this big, and it said that they held 1.44 megs or megabytes. Well, that meant that it held a million bytes, over a million bytes, and so that's when we finally were introduced. Giga means 1 million. Sorry, 1 billion, which is 10 to the 9th power. We were introduced to gigas somewhere in about the year 2000s plus, when we were able to, the consumers were able to buy drives that held 1 billion bits of information, gigabyte drives. At the time I bought a gigabyte drive, I assumed that I wouldn't need anything larger than that to hold everything. Well, now, 2010 plus, we're now up to the terabyte drives, which is 1 trillion. Which is 10 to the 12th power. Okay. Now, beyond the tera, we have the peta. Whereas this is 1 trillion, the peta is a quartillion, which has 15 zeros. Okay. As opposed to the tera, which has 12 zeros. Beyond the, let's see, trillion, this is the quartillion. Next is the exa. The exa is the quintillion, and that has a total of 18 zeros. Beyond the exa is the zeta. So we're from a quartillion, quintillion to a sextillion, and this one has 21 zeros. Okay. After the sextillion comes the septillion, the yada, and the yada has 24 zeros. Scientific notation. Scientific notation is the idea that we have a number 1 through 9 followed by a decimal. Okay, and all the rest of the numbers go behind the decimal. But again, that a single number 1 through 9 is followed by the decimal. Once you have this, you're working now with scientific notation. In order to get the decimal here, we have to move the decimal and gain or lose some power of 10. So let's look at a few examples. Okay, we're going to convert all these into scientific notations. In order to do that, we must put the decimal behind the first number that occurs between 1 and 9. That'll be here, in this case, the 1 here. So the decimal needs to go right behind the 1. Okay, now we're beginning to have scientific notation. Let's rewrite that here. We move the decimal just behind the 1 here, and that's a move of 1. So to represent that, we make that times 10 to the 1. The 1 represents 1 move to get it from the original to the new place, which is the scientific notation. Furthermore, if the original number is larger than the scientific notation, then the index here, or the power, will be positive. Again, if it's larger than the scientific notation, the index or the power here will be positive. Here we want the decimal right behind the 1 again. So 1, 2, 3, 4, 5, that's scientific notation. And to get it there, we have to move 1 time. So put 10 to the first power to represent the move. The original number, 0.12345, is smaller than the scientific notation. If the original number is smaller than the scientific notation, we represent the move with a negative. Here, we have 12,345. The decimal is actually here. We want to move the decimal behind the 1. So this will be a 1.2345. Then times 10. And the number of moves to get the decimal from here to behind the 1 would be 1, 2, 3, 4. So to the 4th power. And the original number is larger than the scientific notation. Therefore, the power will be positive. Here, for scientific notation, we want the decimal behind the first digit. So 1.2345. And then the times 10. What does it take to get the decimal to this place? It takes a total of 3 moves. So this will be the 3rd power for 3 moves. The original problem, 0.001235, is smaller than the scientific notation. Therefore, we will represent this as a negative 3. Next, we want to do a few operations into scientific notation. We're multiplying 2.4 times 10 to the 2nd power times 5.5 times 10 to the 4th power. I'm going to rearrange this using the commutative property of multiplication. I'm going to put the 2.4 here next to the 5.5, multiply those, and then we'll move the 10 to the 2nd power next to the 10 to the 4th power. So I'm rearranging these, or regrouping them. Okay, so I'm going to multiply these two together, which is 2.4 times 5.5. And what I get here is a 13.2. When we multiply common bases, we add exponents. So this will be times 10 to the 6th power. Okay. This solution here is not in scientific notation. I need to have the decimal behind the first digit. So let's move it. So 1.32 times 10 to the 6th power. And we see that the move was 1 time, so we're going to add a 10 that has a 1 for the move. Furthermore, the original 13.2 is larger than the scientific notation of 1.32, so that move will count as positive. Then these two can be placed together, and we get our final answer of 1.32 times 10 to the 7th power. And so this is your scientific notation solution. Next, we have a 0.5 giga and a 1.4 mega. Okay, the giga is represented by times 10 to the 9th power, and the mega is times 10 to the 6th power. Okay, again, I'm going to rearrange these. I'm going to take the 0.5, multiply that times the 1.4, and put the 10 to the 9th power times the 10 to the 6th power. Put those together. And when I multiply this, I'm going to get 0.7. And when I multiply these, I'm going to get times 10 to the 15th power. Okay, so everything now is multiplied. I want this in scientific notation, so the decimal has to go behind the 7. So this will be 7.0 times 10 to the 15th power. And because I switched it to scientific notation, I have a times 10. And there was one move, so this will be 10 to the 1st power to represent that one move. The original problem, 0.7, is smaller than the scientific notation of 7 point. So this will be a negative 1. And combine those together, we get times 10 to the 14th power. Okay. Next. Okay. What we have is 0.5 petas. The peta is times 10 to the 15th power. So 0.5 times 10 to the 15th, and then divided. That's going to be divided by 1.4, and we have a tera, which is times 10 to the, I believe, in 12th power. 12th power. Okay. All right, I'm going to rearrange these, and I'm going to put these two together and divide them. So this will be a 0.5 divided by 1.4, and this over here will be a 10 to the 15th power divided by 10 to the 12th power. Okay. So I combine these using division. So all these are dividing. So 0.5 divided by 1.4. 0.5 divided by 1.4. And decimals have lots of decimals on that. So 0.357. Let's stop there. And over here, 10 to the 15th divided by 10 to the 12th. I'll subtract the exponents, and I get 10 to the 3rd power. Okay. I want this to end in scientific notation, so I'm going to move the decimal over behind the 3. So I get 3.57. And times 10 to the 3rd. Then for the move, since it was just one move, this will be 10 to the 1st power. And the original 0.357 is smaller than the scientific notation of 3.57, so this will be a negative. Okay, then we combine these two, and our final answer is 3.57 times 10 to the 2nd power. And this is the scientific notation that represents the quotient. Okay, let's talk about direct and indirect variation. One note, indirect is also called inverse. Okay, this is read as F varies directly with X, Y cubed, and Z squared. Now you notice that the language here only includes the variables. It never includes the A. That's because the A represents a constant. All variation variation equations have a constant. They're just not named in the process. Only the variables are named. So when the variables are named as direct, all the variables will be multiplied. Then always include the constant or a constant. Here I represent the constant as A, but you represent the constant as any letter. Typically we represent constants with the first letters of the alphabet, A, B, and C. We tend to represent variables with the last letters of the alphabet, X, Y, and Z. Okay, the interpretation of this. G varies indirectly with X squared and Y. And again, you notice that this language right here never included a constant. So inversely implies that that this is located in the denominator or being divided by. Furthermore, here we have H varies directly with X squared and Y, but indirectly with Z to the 3rd power. So since these are in the numerator, it varies directly with X squared and Y. Z is in the denominator, so it varies inversely with that one. And again, we must include a constant. Even though the language does not speak of a constant, the constant must be represented. Okay, solving problems with variation equations. Number 1, force varies directly with the mass of an object. A falling object has a mass of 50 kilograms, has a force of 400. Solving variation equations. Number 1. A force varies directly with the mass of an object. A falling object of mass 50 kilograms has a force of 490 newtons. Find the variation formula. First, we see that the force varies directly with the mass of an object. So we'll use F for force, and it varies directly with the mass of an object, so we'll use M for the mass. Okay. Now, even though they didn't say it, there is a constant here we have to represent. So I'm going to use the letter A to represent the constant. So that's going to be added. Alright, furthermore, we're told that a falling object has a mass of 50 kilograms and a force of 490 newtons. So the force is 490 when we have a mass of 50. We're asked to find the variation formula. Well, to do that, I'm going to solve for my constant A by dividing both sides by 50. I find that A equals about 9.8. Now that I know what my constant is, I will now put the value of my constant into my formula, 9.8 M. And this is the variation equation with the actual constant in it. Number 2, the area of a circle varies directly with the square of its radius. If a circle has radius of 20 centimeters, its area will be 1,256 centimeters squared. Find the variation formula. Okay, the area of a circle varies directly with the square of its radius. The area of a circle, which is A, we use A for the area of a circle, varies directly with the square of its radius. Well, here's the radius, and here's its radius squared. For the constant, I'm going to use, well, I would use A, but I don't want to confuse with this A. So, well, we'll use a lowercase a. So there's my constant. And it varies directly with the radius squared. Now, we're told that a circle with a radius of 20 centimeters, there's 20 centimeters, will give us an area of 1,256. Okay. Well, solve for A, I'll start by squaring to 20. And we'll get 400. Then I'll divide both sides by 400. And 1,256 divided by 400 is going to be 3.14. Okay. So this is our A, our constant. So our formula is area equals the constant 3.14 times the radius squared. And that's our variation equation. Number 3. The speed of a car is inversely proportional to the time it takes to travel. If a car traveling 60 miles per hour arrives to Valencia in 30 minutes, find the variation formula. Okay, the speed of a car is inversely proportional to the time it takes to travel. So, let's represent speed with the letter S, but it's inversely to the time. So let's use T for time, but we'll put that in the denominator. What goes in the numerator is the unknown constant. Okay, now, a couple things. We are told that speed is 60 miles per hour. We're also told the time is 30 minutes. Okay, now we have a problem already. We cannot put 60 and 30 into the problem because this is being represented as part of hours, but this is represented with minutes. They have to be the same units. So what I'm going to do, I would need to either change everything to minutes or everything to hours. I'm going to choose to turn everything into hours. So time, if I want hours, this will be 30 minutes out of 60 minutes. This is a full hour, 60 minutes. 30 minutes is only a portion of it. So what I end up with is 0.5 hours. So now I'm going to use 60 miles per hour and 0.5 hours. So 60 for the S and 0.5 here. Okay. Now I'm going to solve for A by multiplying both sides by the 0.5, and that'll give me 30 here and A there, and this cancels. As a result, giving us S equals 30 all over time. And there's our variation equation. Okay. Number 4, I want you to solve. It says that the gravitational force is directly proportional to the product of the mass of two objects and inversely to the distance squared between the objects. The mass of the Earth and the Moon are 5.98 zetas, kilograms, and 74.8 yada, kilograms, respectively. The distance between the two masses is 0.384 million kilograms. And the gravitational force between them is 202 yada newtons. Find the variation formula.